Hello everyone. We're going to be taking a look at a pretty interesting problem, and that is a circle inscribed within a parabola and trying to find the area between the circle and the parabola. And at first glance, this doesn't look like this would be a very difficult problem for us, but in fact, it involves aspects that require us to think about the problem and some level of detail before we can really tackle it properly. Now, first off, we see that we're going to have to parse this problem into several different problems, in fact. And basically, what we're going to do is take a look at this problem as a difference between several different areas that we've constructed. And the first area that we will be constructing is the area of the rectangle of the intersect points. And that would be that point xy and negative xy. And because of the symmetry of the problem, all we have to do is take a look at the right side of the problem, the right side of the y-axis, and then double everything. That would make it easier. But I'm drawing the entire problem out to show you, in essence, what it really means. So we have a rectangle that's formed by the points of intersect with the circle and the parabola, and that leaves other areas that we're going to have to solve for in order to find that shaded area, the area between the circle and the parabola. And if you notice here, we have the area of an arc, area of the circle. When you take a look at the radii lines, the radius lines between the center of the circle and the intersect point, they form an area sweep for the circle, and that area sweep is not all within the rectangle, if you notice that. It is comprised of the two areas that I showed, AC and AT. And then we have the area below the parabola, which I call AP, which is from the axis line to the parabola, and then AT, which is the shaded area. And so AC plus AT plus AP equals the area of that rectangle. And so when we take the area of the circle between the 2 points xy and negative xy, we have to remove that portion of the triangle that results at the top, that area AT. So we have a pretty interesting problem, and I've written out in general what we're going to be doing. We have the area of the rectangle, A sub r equals 2x times y, and the area of the rectangle is also equal to the area of the arc or the circle, AC, as I have delineated, at least that portion of AC that's within the rectangle, that excludes the area AT, plus AI, the area of the shaded portion, and AP, which is the area of the parabola, between the parabola and the x-axis. And so when we rearrange algebraically, we can find that area AI, or that area that we call the shaded area. Again here, I also noted at the very bottom here, I said where AC equals AA minus AT. AA is the area of the arc, or area of that circle between the intersect points, which forms a portion of the circle, not the area of the full circle. And you can see through symmetry that line up top that I drew and will redraw, that arc that I'm drawing there, that's the area of the circle. It's like a pie-shaped area. And we have to subtract the area of the triangle AT in order to get that portion of the circle's area, AC. So that's why AC is AA, area of the circle between whatever angle that's formed. You can see that the intersect isn't straight on the, it doesn't bisect the circle perfectly. There's it forms a wedge, like a pie wedge, and we have to take a difference between the area of that wedge minus the area of that triangle. Now in this slide, the first thing that we see that we're going to have to do is find the center of the circle, the origin of the circle. Now we set up our coordinate system so that the origin of the problem is at 0, 0, or the base of the parabola. And that means that the circle that sits inside the parabola has a center that is in the y direction at location B. So our origin of the circle is 0B with respect to the origin of the problem that we set up. And so we have the equation of the circle, which is x squared plus y minus b squared equals 1. And we have the parabola, which is y equals x squared. And we need these two equations in order for us to find the intersect point. We have to solve for y. And in the case of the parabola, that's simple. In the case of the circle, we have to do a little algebra. And once we solve for b, with the given, we're given the radius is 1 of the circle. That part is given to us in the problem. Once we solve for the center of the circle in the y direction, then we have enough information in order for us to find the intersect point, x and y. And so that's our approach. And once we have x and y, the rest of the problem then becomes a little bit more straightforward for us to figure out. So first we must find b, and then we solve for x and y, the intercept point between the circle and the parabola. So this is what we do in order to find that point B. We have to solve for the intercept. We solve for y on the circle, which is y equals the square root of 1 minus x squared plus b. and we set that equal to y equals x squared. And when we do so, we end up with an equation, x squared plus, in the brackets, x squared minus b squared squared equals 1. And that should be enough information for us to, first off, that is our intercept point for the given condition of the radius being 1. However, we need to find b. So in order for us to find b, we have to take the derivative of the equation, and we're going to take the derivative implicitly. This is implicit differentiation. And if you remember our differential characteristics and properties, if you set the first derivative to 0, you're able to find the maximum or minimum point. And here we're looking for the minimum between the parabola and the circle. And so by doing, we can solve for b. So we took an implicit differential, set it to 0 to solve for the minimum, and then we just carried out the algebra, and we found that x squared is equal to b minus 1/2, and that gives us something to plug back into the original equation that shows the intercepts, which is x squared plus bracketed x squared minus b squared squared, or b squared, equals 1. And once we do that, we're able to solve for x, our intercept point on, between the parabola and the circle. So that is the difference within this problem. That's the trick or the key to this problem. And once we have x, then we can solve for y. And so here I carry out some of the algebra, and we find that b is equal to 5/4, and that's that portion where I'm encircling it with encompassing it by a rectangle. That's the solution of our algebra. We solve for b. B is 5/4, and then once we have b, we can plug that back into the original equation and solve for the x and y. And once we have the x and y, then everything falls out. We'll have the area of the triangle. We will be able to get the angle at which the radii makes to the intercept point, which then becomes the limits for our integration for the circle. And so everything depends upon finding finding b. Now here I plug b back into the original equation to solve for the x-intercept, and you can see here at the top I have x squared plus y minus 5/4 squared equals 1. And by doing a little bit of algebra and using that relationship that we had found, that b was equal to 5/4, I was able to solve for, using the quadratic equation, I was able to solve for x, and x happens to be the square root of 3 on 2. And I we'll then use that information to solve for y by plugging square root of 3 on 2 into y equals x squared, and I get y equals 3/4. And you'll see that that's within the box up there. And basically, I'm just trying to, I'll use a different color to inscribe the solutions so that they stand out a little bit more readily. First, I think I inscribed the x solution. As you'll see in a moment. I was trying to find the right color. Okay, first I end up circling the angles. I couldn't get the angles without first getting the intercept, because when you set up that triangle, you have to have the base, the height, and we know that the hypotenuse is 1. The base is x, which is square root of 3 on 2, and the height is 5/4 minus 3/4, which is 1/2. And having that, we use 1/2 over 1, which is the sine of phi, and that is 30 degrees. The sine of phi is equal to 1/2, which is 30 degrees, or pi on 6, which leaves us with the other angle being 60 degrees, or pi on 3. And so now that is critical for us to have. You can see on the lower right side that I boxed in the solution x equals the square root of 3 on 2. And that was derived again by solving that quadratic equation. Even though I have a fourth order equation, you can reduce that to basically using the quadratic formula to solve for x squared instead of x. And then up on the upper left, I have y equals 3/4, which I have boxed in. I think I probably erase it and rewrite it. You could see that I've erased it so that you can see it a little bit more readily. So basically what I did there was I took my x answer for the x-intercept between the circle and the parabola, and then plug that into the y equals x squared, and that gives us y equals 3/4. And so that gives us all the information we need to get the angles and to get the intercept coordinates. So now we have everything that we need. So this is the page to take a look at very carefully. First, getting the solution for B, and then getting the intercepts of the intercept coordinates for the circle and the parabola. And once you have all that information, now it becomes a matter of finding the areas. And so we have the area of the rectangle, which happens to be 2 times the square root of 3 on 2 times 3/4. And that's the area of that rectangle, which I showed as a dotted line. Now the area of the triangle is 1/2 the base times the height. That's a fundamentally known formula, equation. We proved it with our calculus. We had a number of calculus videos, and one of them was to prove that the area of a triangle is 1/2 the base times the height in a general way. So we have that, and we have the we can do all of that given the fact that we have the coordinates for the x and y intercept, the origin of the circle, and then we can calculate the base of the right triangle that results. And we have the right triangle down at the bottom of the area of the what we did was once we got the area of the triangle, which is 1/2 the base times the height, and that's square root of 3 on 4. We have that written down at the very bottom right of the page. But AC is the area of the pie, the wedge-shaped pie of the circle, and we have the angular limits that we have gotten from the triangle AT. And so with that, the limit, we were able to get the area of the arc, and subtracting the area of the wedge-shaped pie of the circle from the area of the small triangle, A sub t, we have that boxed in at the bottom center, and that's pi on 6 minus square root of 3 on 4. We have the area AC that we need. So we have the area of the rectangle and the area AC that we need. Now, the area of the parabola is, now we just integrated on the right side and doubled it. So the area between the parabola and the x-axis is given by that double integral, and that's a pretty straightforward deal. And we know our limits of integration in the x direction, which is 0 to square root of 3 on 2. And so the area of the parabola from the x-axis up to the parabola is given as the square root of 3 on 4. So now all we have to do is take the difference. We have everything there. So we have the area of the rectangle is equal to the area C, which we calculated, plus the area sub I, which is the area we're interested in, and the area up between the x-axis and the parabola. And when we rearrange algebraically, we have the solution for the area inscribed or between the circle and the parabola, a sub I, which is 3 times the square root of 3 over 4 minus pi over 6. And that's the final answer. So that's the area of our shaded part of the original problem as it was posed. So, as you could see, this was quite a challenging problem. It wasn't as straightforward as you might think it was, because you have to really think through the problem, especially with the concept of minimizing the equation such that you can find the coordinate B for the center of the circle. That one was, it takes a little bit of, that's a little bit challenging to think through, is to minimize that distance. And that minimal distance then is what allows you to calculate then the intercept points. So it is a fascinating problem from that aspect. It's not as nearly obvious as the problem that we posed prior to this problem. Again, the area is given as 3 square root of 3 over 4 minus pi on 6. We had to parse the problem in such a way that we had different pieces that we had to solve for. We had the rectangular piece, we had the area that was formed by the integration of the circle, but again, that gave us a pie shape, some of which was not inscribed within the rectangle. So we had to take that area away, which is a sub t. And then we have the area below the parabola, which is between the x-axis and the parabola. That's a straightforward integration. And then by difference, once we have the area of the rectangle as a whole, then by differences of the different areas, we can estimate or evaluate exactly what the area sub I is. So there were quite a few dimensions to this problem that weren't necessarily straightforward. And the key, again, is to set the intercept, which is making, solving for y in a general sense, using b as the origin of the circle. So we have y minus b, and then solving for y and making that equal to y equals x squared, and then minimizing that resultant equation to get the value for b, upon which the rest of this entire problem hinges.